Okay, welcome back. In this video I'm going to talk about the underpinnings, basically in really brief detail how the software basically models travel. And you can, if you just want to look at the results of the software, you can safely kind of skip this video, but you probably should care about how it calculates things under the hood at least a little bit. I'm not going to go into lots of equations or anything, just give you the basic flavour for how the software calculates travel demand. So, as we saw in the earlier video, the whole city is divided up into these grid cells. And you've got some grid cell here, A, and you've got a whole bunch of other grid cells. Let's call that one B, let's say. And A has a certain number of activities, and B has a certain number of activities. So let's say A has 15,000 activities. And B has 5,000 activities. Now, a fundamental assumption in the software is basically that the number of trips, both to and from each grid square, is proportional to the number of activities. So in this case, because A has 3 times as many activities, there are going to be 3 times as many trips to A and 3 times as many trips from A as there are from B. So the number of trips to and from each grid cell is fixed, if you like, by the number of activities in that grid cell. Now that doesn't tell you, of course, about where those trips are to or from. So you know that there are a certain number of trips. Let's say there are X trips from A to various other places, but you don't know where they go to exactly. That's got to be determined later, depending on the relative cost of getting to all these different places. So you don't know in particular how many trips there are from A to B, or vice versa. Not yet, anyway. But what we do know is the number of activities in each of these squares, and the number of activities determines the total trips from and the total trips to. So that gives us some constraint later on the trips to and from. So we know the sum of all these trips from A must be 3 times, in this case, the sum of all these trips from B, just because A has 3 times as many activities. Okay, so let's see in a little bit more detail how that might work. So we have A, and we have some potential destinations. So I'm just going to consider trips from A to, let's say there's B and there's C as potential destinations, and of course every other grid square in the whole city is a potential destination. So really this calculation is going to get repeated. The thing I'm going to go through now for just B or C really is done across the whole city, all possible destinations, but just to keep it simple, I'm going to consider just 2 destinations and show you how basically travel is calculated between those 2. So we have A, we know the number of activities in A, and we know the consequently number of trips from A. So the total number of trips, let's say for example there are 10,000 trips from A. We don't know where they go yet. We don't know if they go to B or to C or to some other location, Z, whatever. Now, and of course that's what we want to work out. We want to work out both how many trips there are to B and C and everywhere else, and we want to know what the mode is for each of them as well. Is it by car? And that's what we're going to do here basically. So but we will calculate mode, but for the moment let's forget about mode and let's just work out the number of trips, or see how we'd work out the number of trips. Okay, so again we have this A and B, C, and we know the number of trips from A. Now we also know the number of activities in B and C. So that's what you specify when you describe the city. So we know B, let's say, has 10,000 activities, just for argument's sake, and let's say C is smaller. Let's say it has 5,000 activities. Now the number of, in terms of destinations, B is going to be more attractive than C because it's basically got more stuff there. So there's twice the number of activities. That means, you know, because activities is this generalization of stuff that you might want to visit. It could be it means it's got more people you want to visit, more shopping opportunities, cafes, recreation, all that sort of thing. So B is more appealing because it has more activities. And in the model, the attractiveness of B is basically linear in the number of activities. So the attractiveness of every zone is linear in the number of activities. And there's a parameter that tells you how attractive each one is, and the default, you can fiddle with it, but by default it's going to be the attractiveness. Let's call that no, let's not call it A. The attractiveness of B, or the value, let's say, of B is 0.00075 times the number of activities in B. Number of activities at B. So B has 10,000 activities, so that would mean the value of B is 7.5. Now, that value it's not really a dollar value, it's like a utility of B, but just to keep things easier, I'm going to talk about everything in terms of generalized cost. So there's going to be a generalized value of, in this case, $7.50 for traveling to B, and that's the implied value of someone going to B, so the value of the activity bundle at B. And there's going to be some costs associated with getting to B as well, but let's not worry about that. So far we say the value of B is $7.50, and by the same logic the value of C as a destination is it's going to be $5. So I'm talking about this in terms of dollars, but if you read the manual, it's really, you think about it in terms of utility, and then the costs getting there are generalized costs, but I really don't want to go into that now. Let's just think of it in terms of dollars for B and C, visiting B and C. It's $7.50 value and a $5 value for visiting C. Okay, so we know the value of getting to B and the value of getting to C, but we don't know the cost. But, you know, we can easily work that out. Basically, there's some distance that you have to travel, and let's just consider one mode. So let's just consider car for now, and we'll worry about the other modes later. So, traveling by car from A to B, let's say it takes half an hour to get there. Half an hour, and let's say we value travel time at half the wage rate, and we add some costs in for wear and tear, and maybe some costs in for parking. But we come up with a total cost, or a total generalized cost of getting from A to B of, let's say it's $7, and that's time costs and wear and tear, whatever costs you want to include, and you can choose what gets included later on, and I'll talk about that when we talk about the parameters that you have to specify for the model. But basic thing you need to take away at this stage is that there's some cost, and that cost involves both dollar costs and time costs. But let's say everything's been translated into a dollar generalized cost. So there's a cost of getting to B, $7. And let's say the cost of getting to C is it's $5. Okay, so if there were only two destinations, B and C, we know the value of each of the destinations, and we know the cost of getting to each of the destinations, assuming for the moment just one mode. And so we can use this information to get the net value, that is the intrinsic value of the destination minus the cost of getting there, for each destination. So from A, the net value of B is $7.50 minus the $7 cost of getting there, so it's 50 cents. And the value of C, the net value of C, I don't know what I do, I'll add a prime or something like that to the b. The net value of c is 0. Now don't get hung up about whether these are positive or negative or 0 or whatever. There's no special implication for a value of 0. It doesn't mean, for example, that people will not travel if the value is 0 or less than 0. All that matters is the relative value across all possible destinations. So in this case, since we're considering just 2 destinations, B and C, and there's only one mode possible, which is car for the moment, there are only 2 possibilities. And so the relative value determines how much people from A travel to B as opposed to C. And the exact way that's calculated is going to be, it's going to be e to the 0.5 all on e to the 0.5 plus e to the 0. So that's the proportion of trips from A that will go to B. And the proportion of trips from A that will go to C is just going to be the same thing, but with the relevant number switched around. Plus e to the 0. That's meant to be an e to the 0.5 on the bottom there. So basically it's a discrete, a multinomial legit model where the utility of each destination is this net value variable. And so based on that calculation, you work out that of all the trips from A, this isn't the actual number, I haven't done the calculation, but let's say of all the trips from A, 70% go to B and the other 30% go to C. Okay, so that's how you would do it with one mode and just 2 possible destinations, but hopefully it's pretty easy to see that that generalizes to an arbitrary number of destinations. So you can repeat the same calculation for all possible destinations, for all possible modes. I'll talk about the modes in a minute, but yeah, hopefully that's clear. It's the key really message to take away is that the destination choice is determined entirely by this net value. And you think of that net value as a intrinsic value of a destination combined with the cost of getting to that destination. And that cost, as I said before, is a generalized cost and includes both dollar costs, time costs, parking costs, all that sort of stuff. So hopefully that gives you the basics of the destination choice. And that calculation is repeated for all origins. So from that we could get all destinations. But I might talk a little bit more in the next video about the mode split exactly.